So you've already seen what it means to measure a quantum state in a given basis. This module is about the most general kind of measurements that can be performed on the quantum state. So the formalism of measuring a state in a basis doesn't let you answer all possible kinds of questions that you might want to ask about a quantum system. For example, imagine that your state is described by a density matrix, ρAB, that's over two systems, A and B. Then what happens if you want to measure only system A? What is the probability of obtaining a certain outcome, and how will the state on B be affected by the result of the outcome of the measurement performed in system A? This is a kind of question that we'd like to answer. Another question that you might want to ask is, what if I want to measure a d-dimensional quantum state using a measurement that has, let's say, only two outcomes, a yes-no kind of measurement? So far, we only know how to measure in a basis, and choosing a basis requires making a choice of d possible vectors, which will lead to d possible outcomes. Another question that's a natural one is to ask if all measurements necessarily have to completely destroy the state that they're performed on. This, we've seen that measuring in a basis, after you've performed the measurement, the state is projected on the basis vector that is consistent with the outcome that you obtained. Is this completely necessary? Could you make a weaker kind of measurement that only perturbs the state a little bit? So the goal of this module is to answer all three of these questions by giving you the general formalism of measurements on quantum states. First, let's review briefly what you've seen before. So the first thing that you learned is how to measure pure states. So let's imagine that we're given a pure state described by a unit vector in d-dimensional complex space. And now we measure this state in a certain basis, so we choose a basis B of c to the d. And we saw two rules about this measurement. The first is, what is the probability that we obtain a certain outcome? And the probability that we obtain the outcome B is given by the squared overlap between the basis vector B and the state psi. And the second thing we've seen is that what happens to the state after it's been measured. And this, you know, that if the outcome of the measurement is B, then the state gets projected to the basis vector B. So that's for pure states. Now we also saw what happens when you measure mixed states described by a density matrix, ρ, which now is a positive semi-definite matrix that's a d by d matrix. Again, we can choose a basis B, and the rule is that the probability that we obtain the outcome B when we measure the state ρ is given by the overlap between B and the density matrix ρ. We saw a different way to write this expression as the trace of a product between the rank 1 projection on B and the density matrix. And same thing as before, once the measurement has been performed, the density matrix is projected onto a rank 1 density matrix that is simply the projection on the basis vector B. All right, so that's for basis measurements. Let's learn about general measurements now. So the most general kind of measurements in quantum mechanics are called positive operator valued measure. And often we just abbreviate this. We say POVM. So what's a POVM? How is it specified? It's given by a list of matrices. These matrices are d by d, m1 up to mk. So there's not necessarily d of these matrices. There could be d, there could be more than d, there could be less than d. And there's two conditions that these matrices have to satisfy. First of all, each of them should be positive semi-definite. What this means, if you remember, is that mi should be a Hermitian matrix, and moreover, it should be positive. One way to characterize this is to say that for every vector phi in CD, it should be the case that the overlap of phi with mi is positive. So that's one possible characterization of a positive semi-definite matrix, and in previous modules and also in your problem sets, you saw all the other characterizations. For instance, an equivalent characterization is that mi is Hermitian and all its eigenvalues are non-negative. So that's the first condition. The second condition is that when you sum all the matrices, you should obtain the identity matrix. So given any set of matrices that satisfy these two conditions, that specifies what's called a POVM. And now I have to tell you, suppose you're given a state described by a density matrix Rho and a POVM described by matrices M1 up to Mk. What is the rule? What happens? What outcome do you get? And what happens to the state once you've obtained a certain outcome? So the outcomes, they correspond to the matrices. So we have k possible outcomes, and the probability of obtaining a certain outcome I is given by the trace of the product of the matrix I with the density matrix Rho that we're measuring. So that's the rule. The first thing to check is that this rule makes sense. So we want these probabilities to be probabilities, meaning they should be non-negative, and we want them to add up to 1. So let's check that this is the case. First of all, that they're positive. So you know that a density matrix Rho I can always decompose as a mixture of pure states, like this, where the pi are positive and they sum to 1. Let me use a different index j here so that it doesn't clash with the index j of the matrices. So now if I compute the trace of mi Rho, this will be equal to the sum over j of the trace of mi pj psi j, where I'm using linearity of the trace here. And this we can rewrite as the sum over j of pj overlap of psi j mi psi j, which is positive because all the terms are positive. The pj's are positive and these overlaps are positive by the definition of mi being positive semi-definite. So that's for the first check, passes. Second check, the probability should add up to 1. Let's verify this. So if I compute the sum over I of trace of mi Rho, I can put the summation over I inside the trace because the trace is linear. So this will be equal to the trace of the summation over I of mi Rho. And now we can use the second condition for mi to define a POVM, which is that the sum of the mi should be equal to the identity. So I get the trace of the identity times Rho, which is just the trace of Rho, and because Rho is a quantum state, the trace is equal to 1. So second sanity check passes. Good. At least what we've defined is a valid probability distribution. So this rule here, which tells you what the probabilities are for obtaining certain outcomes, is called the Born rule. And that's one of the most important rules in quantum mechanics. So now we've seen two different rules. We've seen what happens when you measure a state in a basis, and now I'm saying that there's a more general formalism called POVM that you can use in order to measure quantum states. And we have to check that the two of them are compatible. So let's see how measurements in a basis can be formulated as a special case of a POVM. So let's take a state Rho, and let's take a basis B. And now for each B, let's define an operator MB, which is equal to the rank 1 projection on the vector B. So now this operator is positive semi-definite. One way to check that is that it's clearly Hermitian, and if I look at the inner product, the overlap of MB on any state phi, then I will get the squared inner product between B and phi, and this is clearly positive. So MB is positive semi-definite. And I can also check that if I sum over all B of the MBs, I will get the sum over all B of these rank 1 projectors. And using that B is a basis, it's not hard to verify that this is equal to the identity matrix. I leave this to you as an exercise, but one way to check it is to verify that the overlap of any state with the identity or with this sum over B of BB is equal to 1. And you'll be able to verify that this is the case simply by using that B forms a basis. So here we are. Given any basis, we can define a POVM given by these MB. And now we have to check that the Born rule, the measurement rule for general POVMs, gives you the same rule that we saw for measuring in a basis. So let's verify this. So the Born rule says that the probability of a certain outcome B should be equal to the trace of MB times Rho. This is equal to the trace of rank 1 projections on B times Rho, which is simply the overlap of B with Rho. And we recover the rule for basis measurements. So this passes. Indeed, POVMs are a generalization of basis measurements. So now I've told you about the rule that says which outcome will be obtained when you measure a state using a POVM. I haven't told you yet about how the state evolves. What is the post-measurement state like? So let's see this now. So it turns out that if you're simply given the description of a POVM, given the measurement operators M1 up to Mk, this doesn't give you enough information to decide what exactly is the post-measurement state. There's still what we call a unitary degree of freedom. In order to completely specify the post-measurement states, you need to be given a little bit more than the m's. You need to be given what are called cross operators associated with m. So what is a cross operator? In general, this is going to be a d prime by d arbitrary matrix, and d prime is also arbitrary. It could be bigger than d, could be smaller than d, but the condition is that if you look at ei dagger conjugate transpose times ei, this should be equal to mi for all I. So given the mi's, any matrices for any d prime that satisfy this condition are called cross operators associated with mi. And now once you've specified the cross operators, this specifies the post-measurement state. And the rule is that if you observe the outcome I, then the state ρ becomes the state ei ρ ei dagger renormalized. So that's the rule for the post-measurement state. Let's check that it makes sense. So what kind of sanity checks could we perform? Well, we want the post-measurement state to be a state. In particular, this should be a density matrix. It should be positive semi-definite. Why is it positive semi-definite? Because ρ is positive semi-definite, and we conjugate it on the left and on the right by an operator, ei, and its conjugate transpose. This is always going to be positive semi-definite. Since we divide by the trace, we get a density matrix, a positive semi-definite operator that has trace 1. So that check passes. The other thing we could check is that this rule for post-measurement states is compatible with the rule for post-measurement states that we've seen for basis measurements. So suppose that m is a POVM associated with a basis measurement, and that we choose the cross operator. So in that case, I will have mb, the projection on b, and a simple cross operator I can choose is eb to be, again, the same thing as m. So in that case, ρ should be projected to, should be b, ρ, and again, projection on b, divided by the trace of this, which is the overlap of ρ on b. And you can verify now that the denominator here and the numerator, same number, they cancel out. And so what I get is just the rank 1 projection on B as it should be. So here we are. We've completely generalized the rule for making measurements, both in terms of describing the probability of the outcomes and in terms of describing the post-measurement state.